factors. We've kind of been able to do that with synthetic division already to this point, but some of these are just factorable and we won't even need to use synthetic division. In this particular case, I'm going to show you a way that I was taught in calculus how to use substitution to make things a little bit easier and why this always works. This is x to the fourth, x squared, and x to the 0. What does that look a whole lot like? But if we think about the terms of the degrees, this goes from 4 to 2 to 0 versus 2 to 1 to 0. What does that look a lot like? What's the thing we normally factor? Quadratics. Okay. So this is very, very similar to a quadratic when it goes from 4 to 2 to 0. And so in calculus, I don't know why they choose the letter U, but they choose the letter U a lot when they do their substitutions. So we can say that U equals x squared. And so then I can just substitute this in. And so if I was demonstrating with number 8, I would say that instead of x to the fourth, I could call that U squared. Because x squared squared is x to the fourth. And then I could say this is plus 21u minus 100. And so now when I look at that, I go, oh, hey, that is a quadratic. I know exactly how to factor that. What's going to multiply to negative 100 but add to 21? What's our factors of 100? 25 and 4. Good. Okay, so we'll have plus 25, and we'll have negative 4. And now we just go back and substitute the u with x squared. So now we know that this is actually just x squared plus 25 and x squared minus 4. So that's one of those weird steps of why it always works. After a while, you may not use that substitution step. You may, every time you see one of these, go, oh yeah, instead of having an x in the front of each of these, it's going to be an x squared instead. But if we use substitution, this is kind of one of those things that helps prove why that always works. Then I want to make these into linear factors because right now they're both still quadratic factors. So I can go find the zeros of each. The zeros of this one would be x squared minus 4 equals 0. Or x squared equals 4. Or x equals plus or minus 2 when I take the square root of both sides. Okay? So my two linear factors I'll get from here are going to be x minus 2 and x plus 2. So there's linear factors. On this side, we have the x squared plus 25 equals 0. So x squared equals negative 25. What's going to happen when I take the square root of both sides? We're going to end up with, what happens when you take the square root of a negative? Imaginary. We get I. Okay, here comes those complex roots. Okay, so now we're going to end up with x is going to equal plus or minus 5i. Okay, and this is something that we're going to see over and over. This is kind of a key piece of today. If you have one complex root, you must have two. There's always the positive and there's always the negative of it. So anytime we're doing stuff today that you see, oh, hey, there's a complex root, know that the conjugate is also there, the positive and the negative. Okay? So this would give us linear factors of x minus 5i and x plus 5i. Let's see if I can fit this inside here. Yeah. Okay. So there's my four linear terms, my linear factors of this polynomial, and my four zeros helped me get to those linear factors. So I know x equals plus or minus 5i and x equals plus or minus 2. Those are my four zeros. Okay. The other ones you're going to see today are like cubic type ones. And I'm just going to make something up because I don't remember exactly what they are.
It's plus x squared. Minus 1.
Minus. Just minus 1.
Minus 1.
It's x cubed plus x squared. Minus x.
Minus x minus 1.
Minus x minus 1. Okay. So these ones, you'll see if you go back and look at the way the book teaches you to do it, you can use synthetic division to help you find these. Otherwise, the book is going to give you just special ones today where you can cut it in half like we would with our factoring quadratics with an a value that's greater than 1 or something different than 1. You can factor the left, you can factor the right, and then you'll end up with something that's an x squared. Typically, that's where your imaginary roots will come, and then there'll be a linear factor that comes out as well. Okay, so you can do those as well by splitting it down the middle and factoring the left and right side of that wall. All right, next piece we're going to see is we're going to talk about factoring polynomials completely and write any repeating factors in exponential form, then name all the zeros and their multiplicity. Has anybody dealt with multiplicity before? Okay. So what we're looking at is if a 0 happens multiple times, that's its multiplicity. So for example, let's take a look at 16. As I go to factor this, I go, okay, what's going to multiply to 36, but add to 12, 6 and 6. So we would end up with an x plus 6 and an x plus 6. How many times does that 0 occur so far? Twice, okay? So its multiplicity would be 2. It's happening twice. Okay, over here, what's going to multiply to negative 24, but add to 2? 6 and negative 4. And then negative 4 is just a linear factor that was hanging out here. So now as I look at these and I combine them into exponential form, we'll have x plus 6 how many times? 3. So that quantity is cubed. And then x minus 4, how many times? So that has a multiplicity of 2. So when we go to talk about this, say name the zeros and their multiplicity. X equals negative 6 with a multiplicity of 3. And x equals 4 with a multiplicity of 2. So now I've named my zeros and their multiplicities. Okay, the multiplicities will eventually help us when we go to graph these, because eventually I'll say, hey, here's a polynomial, go find all the zeros, and you'll see some of these have multiplicities where, all right, well, this is a 5th degree polynomial, so it's an up or it's a down up type behavior. It's going to cross through at negative 6, and it's going to bounce at 4. I'll teach you guys this later, but you're going to see it come up. It'll behave like a cubic at that intersection point, and then it's going to come down and it'll bounce at 4. And so we'll be able to create graphs that look roughly like that for sketches. Okay? That's what we'll learn in a couple weeks. But that's why multiplicity is important. So we'll factor things out, we'll give their zeros, and we'll give their multiplicities. All right, and then lastly, what we're going to take a look at today is we're going to find polynomials given a real coefficient and the non-real coefficients, the complex ones. So all real coefficients are given today. Some of them may have multiplicities of more than just 1. And then we're going to look at complex ones. And this comes into that idea that if I have one complex, I must have 2. I have the positive and the negative. It's conjugate, so to speak. So when I take a look at something like 20, I know it's a degree of 3, so how many total zeros will it have? 3. Good. Okay, so a degree of 3 has 3 zeros. They could be real, they could be non-real. And so in this case, my real 0 is negative 5, so I know I have the factor x plus 5. I know I also have x equals negative 3i, so I also know I have the factor x plus 3i. What's my third 0? We're going to write this the rest of the way out. I have a real 0 given. I have a one complex 0 given. I need a total of 3 zeros.
Don't you have to do the positive and negative of the complex one?
Excellent. So my other 0 is positive 3i, which gives me x minus 3i as the other factor. So again, these will always come in pairs. If you have a positive, you have a negative. So if you have x plus 3i, you have its conjugate as well, which is minus 3i. Okay, and so that will help us find the rest of them. The other ones you'll see is maybe it's a degree of 4. So in this exact same situation, if it was degree of 4, we'd have the complex numbers, both positive and negative, but then we would have multiplicity of 2 on this real 0. So we would just square that. Okay. So that's the other stuff you'll see. If you have one complex, you must have 2. If you have a real and you're short 1 because of the degree, you're going to have a multiplicity of 2. So those are some of the things you look at. I believe this is acceptable as far as the answer. Otherwise, if it ever tells you to multiply it the rest of the way out, you can talk about how this is x squared plus 9. And then multiply that by the x plus 5. So we would end up with x cubed plus 5x squared plus 9x plus 45. So if it wants you to put it in the standard form, that's how you would get it the rest of the way in the standard form. So this is our function of x. All right, feeling good?